Welcome back to linear algebra. I was going to rewrite my keyboard, but look, we'll just check Anki just in case, even if you have any flashcards due. Okay, no flashcards due. All right. So then what did we learn about yesterday? Okay. We learned about equivalence theorem. This is that if we know, or basically the statements that are equivalent, a matrix is, or we can know is true. Anyway, all right. If one of these is true, all of them are true. If one of them is false, all of them are false. That's what it means by equivalence. A matrix is invertible. The row echelon form, reduced row echelon form, is the identity matrix. The formula AX, X being a column vector, equals 0. So homogeneous linear system only has the trivial solution. And fourth one, the matrix can be represented by a product of elementary matrices. If any of these are true, then they're all true. If any of them are false, then they're all false, okay? One other thing we did was determine or find an algorithm for finding the determinant, not the determinant, the inverse of a matrix. Very simply, you partition an identity matrix next to the matrix or within the matrix, and then you just solve using you reduce the original matrix down to reduced row echelon form into an identity matrix, and while you're doing that, you're using the same elementary row operations on the identity matrix. So once you get the original matrix to the identity matrix is now the inverse. What was the identity matrix is now the inverse of the matrix, because the same sequence of elementary row operations that gets one matrix into the identity matrix is the same that will take the identity matrix to the inverse. And if you can't reduce a matrix down from reduced row echelon if you can't reduce a matrix down into the identity matrix, right, then it's basically not invertible. And this is, again, this equivalence theorem is for square matrices, n by n matrices. So I think that's everything. If so, we're going to be jumping right back in into it. All right, partition matrix, same sequence of elementary row operations that reduce it. Okay, find inverse matrix, partition, use elementary rows. Okay, you can know a matrix isn't invertible. Okay, you can tell if a homogeneous system has a non-trivial solution by finding if you can reduce the augmented matrix to I. Simple enough. What is this section about? Inverting a method for inverting matrices. What do you think it's about? It's a method using elementary row operations and a partitioned matrix to find the inverse of a matrix. All right. That's it. So we're gonna actually start doing practice problems now. Cool enough. Oh, hold up. I think we forgot to do 1.4 flashcards. Anyway, 1.4 flashcards. Let's go ahead and say, what is this section about? Elementary matrices, method for finding inverse matrix the inverse of a matrix and equivalence theory. Theorem, not theory. Theorem. All right, let's quickly check. Have I done these flashcards for 1.4? If not, that's gonna kind of suck. What we'll do instead is we'll do one problem from 1.5 and then we'll do flashcards for the rest of the time. All right. Elementary matrix. Yeah, we haven't done them. Shoot. All right. So I'm gonna do one practice problem, and then I'm gonna work on flashcards for the rest of the time, and then I'll be back to recall in a bit. All right, guys. We finished two problems. Basically, one was asking if it's elementary matrix or not. Another was asking for the elementary row operation that undoes the elementary, or turns the elementary matrix into the identity matrix, and also the matrix itself, the elementary matrix itself, that will turn it back into the identity matrix. And then we completed 8 flashcards from we logged in, created 8 of the 18 flashcards for section 1.4, which was inverses and algebraic properties of matrices. So that's it for today. Good progress made today. I'll talk to you tomorrow. See ya.